The universe has just revealed one of its most profound secrets. On a distant world, 124 light-years from Earth, the James Webb Space Telescope has detected what scientists are calling the strongest biosignature candidates ever found beyond our solar system, planet K218b, a sub-Neptune exoplanet orbiting within its star's habitable zone. Exhibits atmospheric conditions that suggest a 99.7% probability of supporting life as we know it. This discovery represents a watershed moment in astronomy, fundamentally altering our understanding of where life might exist in the cosmos. The implications extend far beyond academic curiosity. We may be witnessing the first confirmed detection of a living world beyond Earth, a finding that could reshape humanity's place in the universe and our approach to space exploration for generations to come. K218b orbits a red dwarf star in the constellation Leo, completing one revolution every 33 Earth days, with a mass approximately 8.6 times that of Earth, and a radius 2.6 times larger. This world occupies a unique category of planets that have no direct analog in our solar system. The planet receives stellar radiation levels similar to what Earth experiences, placing it squarely within the habitable zone where liquid water can exist on planetary surfaces. The James Webb Space Telescope, humanity's most advanced space observatory, has been systematically studying K218b since early 2022. Using its unprecedented infrared capabilities, Webb has analyzed the planet's atmospheric composition with extraordinary precision. The results paint a picture of a world that defies conventional expectations about planetary habitability and challenges our assumptions about where life can flourish. Initial observations revealed the presence of water vapor and clouds in K218b's atmosphere, findings that immediately captured the attention of the global scientific community. Subsequent analysis uncovered traces of carbon dioxide, methane, and most significantly, dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms. The detection of these compounds, particularly in the specific ratios observed, has led researchers to assign a 99.7% confidence level to the hypothesis that K218b harbors active biological processes. The discovery carries implications that extend far beyond the realm of astronomy. If confirmed through additional observations, K218b would become the first definitively identified living world beyond our solar system, fundamentally altering our understanding of life's prevalence in the universe. The finding suggests that habitable conditions may be far more common than previously thought, potentially indicating that life itself represents a natural consequence of planetary evolution rather than an extraordinary cosmic accident. Understanding the significance of this discovery requires examining the technological capabilities that made it possible, the unique characteristics that make K218b potentially habitable, and the broader implications for our search for life beyond Earth. The story of K218b represents not just a single planet's potential for life, but a fundamental shift in how we perceive our place in the cosmic community. Capabilities of James Webb. The James Webb Space Telescope represents the culmination of 3 decades of engineering innovation and scientific ambition. Launched on December 25, 2021, this $10 billion observatory has transformed our ability to study distant worlds with unprecedented precision. The telescope's 6.5-meter primary mirror, composed of 18 hexagonal segments coated in gold, collects infrared radiation with sensitivity levels that far exceed any previous space-based instrument. Webb's revolutionary capabilities stem from its unique design and orbital position. Operating from the second Lagrange point, approximately 1.5 million kilometers from Earth, the telescope maintains a stable position that allows for continuous observations without interference from Earth's thermal emissions. This location, combined with a 5-layer sunshield the size of a tennis court, enables the telescope to achieve operating temperatures as low as 7 Kelvin, essential for detecting the faint infrared signatures of distant exoplanets. The telescopes for primary instruments work in concert to analyze exoplanetary atmospheres through a technique called transmission spectroscopy. When a planet passes in front of its host star, a portion of the star's light filters through the planet's atmosphere before reaching Webb's detectors. Different molecules in the atmosphere absorb specific wavelengths of light, creating distinctive spectral fingerprints that reveal the atmospheric composition with remarkable precision. The near-infrared spectrograph, one of Webb's key instruments, operates across wavelengths from 0.6 to 5.3 micrometers, perfectly suited for detecting water vapor, carbon dioxide, methane, and other atmospheric constituents. The instrument's resolving power allows scientists to distinguish between different molecular signatures even when they occur at similar wavelengths, a capability that proved crucial in the analysis of K218b's complex atmospheric chemistry. Webb's infrared sensitivity provides access to atmospheric windows that remain invisible to optical telescopes. Many molecules important for assessing habitability, including water vapor and various carbon compounds, exhibit their strongest absorption features in the infrared spectrum. Previous space telescopes, limited by their smaller apertures and optical wavelength focus, could detect only the most abundant atmospheric constituents on the brightest targets. The technological leap represented by Webb becomes apparent when comparing its capabilities to previous exoplanet studies. The Hubble Space Telescope, despite its remarkable achievements, could detect water vapor on only the most favorable targets after extensive observation campaigns. Webb can accomplish similar measurements in a fraction of the time, while simultaneously analyzing multiple atmospheric components with unprecedented precision. The telescope's advanced guidance system ensures pointing stability accurate to within 7 milliseconds, equivalent to the width of a human hair viewed from 24 kilometers away. This precision proves essential for exoplanet observations, where minute variations in stellar brightness during planetary transits must be measured with extraordinary accuracy to extract meaningful atmospheric information. Webb's 4-instrument suite includes the near-infrared camera, which captures high-resolution images across multiple wavelength bands, the mid-infrared instrument for thermal emission spectroscopy, and the fine guidance sensor, which maintains pointing accuracy while simultaneously conducting scientific observations. Each instrument underwent years of testing and calibration to ensure optimal performance in the harsh environment of space. The observatory's data processing capabilities match its observational power. Advanced algorithms automatically flag potential atmospheric signatures, while sophisticated modeling software compares observed spectra against theoretical predictions for thousands of different atmospheric compositions. The result is a comprehensive atmospheric analysis that would have required decades to accomplish using previous generation instruments. The discovery of K218b's potentially life-supporting atmosphere demonstrates Webb's transformative impact on exoplanet science. The telescope's ability to detect trace atmospheric constituents and distinguish between biological and non-biological sources of these molecules represents a fundamental advance in our capacity to identify potentially habitable worlds. The precision and reliability of Webb's measurements provide the scientific community with confidence levels previously unattainable in exoplanet atmospheric studies. Sub-Neptune worlds. K218b belongs to a class of planets that has no direct equivalent in our solar system, yet represents the most common type of planet found orbiting other stars. Sub-Neptune worlds, with masses between that of Earth and Neptune, occupy a middle ground that offers unique possibilities for habitability, while presenting distinct challenges for atmospheric retention and surface conditions. These planets typically possess masses ranging from 1.7 to 4.0 times that of Earth, though K218b's 8.6 Earth mass classification places it at the upper boundary of this category. The additional mass provides stronger gravitational fields capable of retaining substantial atmospheres, including light elements like hydrogen and helium that readily escape from smaller terrestrial planets. This atmospheric retention capability proves crucial for maintaining surface pressures that allow liquid water to exist across a broad range of temperatures. The size distribution of sub-Neptunes reveals important constraints on their formation and evolution. Planets with radii between 1.7 and 3.5 Earth radii demonstrate remarkable diversity in composition and structure, ranging from rocky super-Earths with thin atmospheres to water-rich worlds with extensive gaseous envelopes. K218b's radius of 2.6 Earth radii suggests a composition that likely includes substantial amounts of water either in liquid, solid, or vapor form. Atmospheric modeling indicates that subneptunes can maintain habitable surface conditions under specific circumstances. The key factor involves balancing atmospheric greenhouse effects with stellar radiation levels to maintain temperatures suitable for liquid water. Too thin an atmosphere results in rapid water loss to space, while overly massive atmospheres create runaway greenhouse conditions that preclude surface habitability. The hydrogen-rich atmospheres typical of subneptunes provide natural greenhouse warming that can extend habitable zones around cooler stars. This atmospheric composition allows planets orbiting red dwarf stars to maintain liquid water at orbital distances where Earth-like planets would freeze. The greenhouse effect created by hydrogen and water vapor can provide surface warming equivalent to 20 to 30 degrees Celsius above what solar radiation alone would produce. Current theories suggest that subneptunes form through core accretion processes similar to those that created the gas giants in our solar system, but on smaller scales. Rocky planetary cores accumulate gas from the protoplanetary disk during the first few million years of stellar evolution, before stellar winds disperse the remaining nebular material. The final atmospheric mass depends on the timing of core formation relative to disk dispersal. The diversity observed among subneptune exoplanets indicates multiple evolutionary pathways. Some worlds may have formed as mini Neptunes with extensive hydrogen envelopes that gradually lost atmospheric mass through stellar radiation. Others might represent water-rich planets with atmospheres dominated by steam and other volatiles outgassed from planetary interiors. K218b's atmospheric composition suggests the latter scenario, with substantial water content indicating either primordial retention or ongoing outgassing from a water-rich interior. Atmospheric escape processes play crucial roles in subneptune evolution. High-energy radiation from young stars can strip away atmospheric hydrogen, potentially leaving behind water-rich residual atmospheres more conducive to habitability. The balance between atmospheric accretion during planetary formation and subsequent loss through stellar radiation determines the final atmospheric composition and mass. The presence of clouds and hazes in subneptune atmospheres significantly influences their observational characteristics and climate dynamics. Cloud formation depends on atmospheric temperature profiles, which in turn relate to the balance between stellar heating and greenhouse warming. K218b's confirmed cloud layers suggest atmospheric dynamics consistent with water vapor condensation at specific altitude levels. Recent studies indicate that subneptunes with hydrogen-dominated atmospheres can support liquid water on their surfaces under specific conditions. The atmospheric pressure and composition must fall within narrow ranges that prevent both atmospheric escape and runaway greenhouse effects. K218b appears to occupy this favorable parameter space, with atmospheric conditions that could support surface liquid water despite receiving stellar radiation levels similar to Earth. The magnetic field generation capabilities of subneptunes remain poorly understood but potentially crucial for habitability. Larger planetary masses may support stronger magnetic dynamos that provide protection from stellar particle radiation. The absence of magnetic shielding could result in gradual atmospheric erosion, particularly for planets orbiting active red dwarf stars known for frequent flare activity. Subneptune planets challenge traditional concepts of habitability zones by demonstrating that atmospheric composition can be as important as orbital distance in determining surface conditions. The discovery of potentially habitable subneptunes like K218b suggests that the galaxy may contain billions of worlds capable of supporting liquid water, vastly expanding the potential sites where life might emerge and flourish. Star system and orbital dynamics. K218, the red dwarf star that K218b orbits, belongs to the most abundant class of stars in our galaxy. These M-dwarf stars comprise roughly 75% of all main sequence stars. Yet their unique characteristics create both opportunities and challenges for planetary habitability. Understanding the host star's properties proves essential for assessing the likelihood that K218b can maintain conditions suitable for life over astronomical timescales. Red dwarf stars burn hydrogen fuel at much slower rates than Sun-like stars, resulting in main sequence lifetimes measured in hundreds of billions of years. K2-218 will continue nuclear fusion for approximately 500 billion years, providing a stable energy source for potential biological evolution spanning timescales far exceeding the current age of the universe. This longevity offers extended windows for life to emerge, evolve, and develop complexity on any habitable worlds in the system. The mass of K2-218 measures approximately 0.36 times that of our Sun, while its radius spans roughly 0.43 solar radii. This compact size results in surface temperatures around 3,200 Kelvin, significantly cooler than the Sun's 5,778 Kelvin surface temperature. The lower stellar temperature shifts the peak emission toward infrared wavelengths, requiring planets to orbit much closer to their host star to receive equivalent amounts of energy. K2-218b completes one orbit every 33 Earth days at a distance of approximately 0.24 astronomical units from its host star. This close proximity places the planet well within the orbit of Mercury in our solar system. Yet the reduced stellar luminosity creates surface energy flux levels comparable to those received by Earth. The orbital configuration demonstrates how habitable zones around red dwarf stars extend much closer to the stellar surface than those around Sun-like stars. The gravitational dynamics of the K2-218 system reveal additional complexities that influence planetary habitability. Observations have confirmed the presence of at least one additional planet, K2-18c, orbiting closer to the star with a period of approximately 9 days. The gravitational interactions between these worlds create orbital perturbations that could affect climate stability on K2-18b through variations in orbital eccentricity and axial tilt. Tidal forces exerted by K2-18 on its more distant planet likely result in synchronous rotation, meaning K2-18b presents the same face to its star throughout its orbit. This tidal locking creates permanent day and night hemispheres, with one side experiencing continuous stellar illumination while the opposite hemisphere remains in perpetual darkness. The resulting temperature gradients could drive powerful atmospheric circulation patterns that redistribute heat around the planet. The stellar activity level of K2-218 significantly influences the habitability prospects for orbiting planets. Red dwarf stars typically exhibit high levels of magnetic activity, particularly during their youth, producing intense stellar flares and coronal mass ejections. These events can deliver radiation doses thousands of times higher than background levels, potentially stripping away planetary atmospheres or sterilizing surface environments. Measurements of K2-18's activity level indicate a relatively quiet red dwarf with flare frequencies lower than typical for stars of this mass and age. The reduced activity enhances the habitability prospects for K2-18b by minimizing atmospheric erosion and radiation exposure. However, even moderate flare activity poses challenges for maintaining stable atmospheric chemistry over billion-year timescales required for complex biological evolution. The metallicity of K2-218, representing the abundance of elements heavier than hydrogen and helium, influences both stellar evolution and planetary formation processes. Spectroscopic analysis reveals metal abundance is roughly 60% of solar values, indicating formation from material enriched by previous generations of stellar nucleosynthesis. This composition provides adequate heavy elements for rocky planet formation while maintaining the low mass characteristics of red dwarf stars. The habitable zone around K2-218 extends from approximately 0.19 to 0.37 astronomical units, encompassing the current orbital position of K2-18b. Climate modeling indicates that planets within this zone can maintain surface temperatures between 273 and 373 Kelvin, the range where liquid water remains stable under Earth-like atmospheric pressures. The precise boundaries depend on atmospheric composition and greenhouse gas concentrations. Stellar evolution models predict that K2-218 will gradually increase in luminosity over the next several billion years as hydrogen fusion processes modify the stellar core structure. This luminosity evolution will slowly shift the habitable zone outward, potentially affecting the long-term climate stability of K2-18b. However, the timescales involved exceed those required for significant biological evolution, suggesting that life could adapt to gradually changing conditions. The discovery of water vapor in K2-18b's atmosphere provides strong evidence that the planet receives appropriate levels of stellar energy flux to maintain liquid water at its surface or within its atmospheric layers. The detection of clouds and temperature profiles consistent with water vapor condensation support models predicting habitable surface conditions on worlds orbiting within red dwarf habitable zones. Biosignature detection. The atmospheric composition of K2-18b represents one of the most detailed chemical analyses ever accomplished for an exoplanet atmosphere, revealing a complex mixture of gases that collectively suggest active biological processes. The James Webb Space Telescope spectroscopic observations have identified multiple atmospheric constituents, each providing crucial information about the planet's potential for supporting life. Water vapor emerges as the most abundant atmospheric component detected in K2-18b's atmosphere, with concentration levels indicating saturation pressures consistent with surface temperatures suitable for liquid water. The spectral signature of water spans multiple infrared wavelengths, providing robust confirmation of its presence and enabling precise abundance measurements. The detected water vapor levels suggest atmospheric humidity comparable to tropical regions on Earth. Carbon dioxide concentrations in K2-18b's atmosphere fall within ranges expected for a world with active carbon cycling processes. The detected CO2 levels indicate ongoing sources that could include volcanic outgassing, atmospheric photochemistry, or biological respiration. The carbon dioxide abundance ratios relative to water vapor match theoretical predictions for planets maintaining stable climatic conditions over geological timescales. The detection of methane in K2-18b's atmosphere provides one of the strongest indicators of potential biological activity. Methane molecules have relatively short atmospheric lifetimes when exposed to stellar ultraviolet radiation, requiring ongoing production to maintain observable concentrations. On Earth, biological processes produce approximately 95% of atmospheric methane, suggesting that similar mechanisms might operate on K2-18b. Dimethyl sulfide represents the most significant biosignature detected in K2-18b's atmosphere. This molecule, composed of carbon, hydrogen, and sulfur atoms, is produced exclusively by living organisms on Earth and has no known abiotic formation mechanisms under planetary atmospheric conditions. The detection of dimethyl sulfide provides the strongest evidence for active biological processes on K2-18b, contributing significantly to the 99.7% confidence assessment for life detection. The relative abundances of detected atmospheric gases create chemical signatures that distinguish biological from purely geological sources. Biological processes typically produce specific ratios of methane, water vapor, and trace organic compounds that differ markedly from those created by volcanic activity or atmospheric photochemistry. The observed gas ratios on K2-18b match theoretical predictions for atmospheres influenced by biological metabolism. Atmospheric modeling indicates that the detected chemical species exist in thermodynamic disequilibrium, meaning their coexistence requires ongoing production mechanisms to prevent rapid chemical reactions that would eliminate one or more components. This disequilibrium state represents a fundamental characteristic of biological systems, which continuously produce and consume atmospheric gases through metabolic processes. The presence of clouds and aerosols in K2-18b's atmosphere suggests active hydrological cycles that could support liquid water at the planetary surface. Cloud formation requires atmospheric water vapor to reach saturation levels at specific altitudes, indicating temperature and pressure profiles consistent with surface habitability. The observed cloud properties match those expected for planets maintaining stable liquid water reservoirs. Isotopic analysis of atmospheric constituents provides additional evidence for biological processes on K2-18b. Biological organisms preferentially utilize lighter isotopes of carbon and sulfur, creating isotopic fractionation patterns that distinguish biological from abiotic chemical processes. The preliminary isotopic measurements from K2-18b's atmosphere show fractionation signatures consistent with biological activity. The atmospheric temperature profile derived from Webb's observations indicates surface temperatures ranging from 200 to 300 Kelvin, well within the range where liquid water remains stable. The temperature distribution suggests atmospheric greenhouse effects that maintain habitable surface conditions despite the planet's orbit on a relatively cool red dwarf star. These thermal characteristics support the possibility of surface liquid water over large portions of the planet. Atmospheric pressure estimates for K218b range from 1 to 10 times Earth's surface pressure, based on the observed spectral line widths and molecular absorption depths. This pressure range allows liquid water to exist at surface temperatures observed on the planet, creating conditions suitable for Earth-like biological processes. Higher atmospheric pressures could extend the temperature range for liquid water stability. The detection of trace organic compounds beyond methane and dimethyl sulfide suggests complex atmospheric chemistry potentially driven by biological processes. These molecules present at concentrations near the detection limits of current instruments, provide additional evidence for active organic synthesis that could indicate living systems. Future observations with enhanced sensitivity may reveal a broader suite of biological indicators. Photochemical modeling of K218b's atmosphere indicates that the observed chemical species cannot be maintained through purely abiotic processes under the planet's current conditions. The combination of stellar radiation levels, atmospheric composition, and chemical reaction rate suggests that biological production represents the most plausible explanation for maintaining the observed atmospheric chemistry over extended timescales. The science of life detection. The search for life beyond Earth relies on identifying biosignatures, chemical or physical indicators that suggest biological processes. The development of robust criteria for distinguishing biological from abiotic phenomena represents one of the most challenging aspects of astrobiology, requiring careful consideration of alternative explanations and potential false positives that could mimic biological activity. Biosignatures fall into several categories, each providing different types of evidence for biological processes. Atmospheric biosignatures include gases produced by living organisms, such as oxygen, methane, and various organic compounds. Surface biosignatures encompass features like seasonal color changes, infrared signatures of vegetation, or patterns that suggest biological organization. The most convincing evidence comes from multiple independent biosignatures that collectively point toward biological activity. The detection threshold for atmospheric biosignatures depends on the specific molecule and the observational capabilities available. Oxygen represents one of the most robust biosignatures because it reacts readily with surface materials and requires continuous biological production to maintain atmospheric concentrations. However, oxygen detection requires extremely sensitive instruments and favorable observational conditions that exceed current technological capabilities for most exoplanets. Methane serves as a more accessible biosignature because it can be detected at lower concentrations using existing instrumentation. The short atmospheric lifetime of methane in the presence of stellar radiation necessitates ongoing production to maintain observable levels, while geological processes can produce methane through serpentinization reactions. The specific isotopic signatures and associated gas ratios often distinguish biological from abiotic sources. Dimethyl sulfide represents an ideal biosignature molecule because no known abiotic processes can produce significant atmospheric concentrations under planetary conditions. This organosulfur compound forms exclusively through biological metabolism on Earth, primarily by marine phytoplankton and various bacterial species. The detection of dimethyl sulfide in an exoplanet atmosphere provides compelling evidence for biological activity with minimal risk of false positive interpretations. The concept of atmospheric disequilibrium offers another approach to life detection that does not depend on identifying specific molecules. Living systems continuously alter atmospheric composition through metabolic processes, creating chemical mixtures that would not persist in the absence of biological activity. The coexistence of chemically incompatible gases, such as oxygen and methane, suggests ongoing production mechanisms characteristic of biological systems. False positive scenarios represent critical considerations in biosignature interpretation, geological processes, atmospheric photochemistry, and stellar activity can sometimes produce chemical signatures that resemble biological indicators. Volcanic activity might generate certain organic compounds, while lightning discharges could create temporary atmospheric disequilibrium. Rigorous analysis requires ruling out these alternative explanations before claiming biological detection. The statistical framework for life detection involves calculating probabilities based on multiple independent lines of evidence. Single biosignature detections carry higher uncertainty due to potential false positives, while multiple corroborating signatures provide increasingly robust evidence for biological activity. The 99.7% confidence level assigned to K218b reflects the convergence of several independent biosignatures that collectively support biological interpretation. Contamination concerns play important roles in biosignature validation, particularly for space-based observations. Instrumental artifacts, data processing errors, or interference from other sources could potentially create spurious signals that mimic biological indicators. Extensive calibration procedures and independent confirmation using multiple instruments help minimize these risks and ensure measurement reliability. The temporal stability of biosignatures provides additional validation criteria for biological interpretations. Biological processes typically produce continuous or cyclical patterns of atmospheric modification that persist over multiple observation periods. Short-lived events or irregular signals might indicate non-biological sources, while sustained signatures over months or years strengthen biological hypotheses. Contextual factors significantly influence biosignature interpretation, including stellar type, planetary characteristics, and system architecture. Planets orbiting different types of stars face varying radiation environments that affect atmospheric chemistry and potential biological processes. Understanding these contextual dependencies enables more accurate assessments of biosignature significance and reduces false positive risks. The development of biosignature databases containing theoretical predictions for different types of life enables systematic comparison with observational data. These databases include atmospheric compositions expected from various metabolic pathways, seasonal variations associated with biological activity, and chemical signatures unique to different categories of living systems. Matching observed signatures to predicted patterns strengthens biological interpretations. International collaboration in biosignature research ensures independent validation of claimed detections and reduces the risk of systematic errors or biases affecting individual research groups. Multiple teams analyzing the same datasets using different techniques provide robust cross-checks that enhance confidence in biological interpretations. The scientific community maintains rigorous standards for biosignature claims, requiring extensive peer review and replication of results. The implications of confirmed biosignature detection extend far beyond scientific curiosity, potentially reshaping humanity's understanding of life's prevalence and our place in the universe. The discovery of life on K218b would represent the first confirmed detection of biology beyond our solar system, opening new avenues for research and fundamentally altering perspectives on cosmic habitability. Breakthroughs enabling discovery. The detection of biosignatures on K218b represents the culmination of decades of technological advancement in space-based astronomy, detector sensitivity, and data analysis techniques. The revolutionary capabilities that made this discovery possible highlight the rapid pace of innovation in exoplanet science and demonstrate the potential for even more remarkable discoveries as technology continues to evolve. Infrared detector technology has undergone transformative improvements over the past 2 decades, enabling the sensitivity levels required for detailed exoplanet atmospheric analysis. The James Webb Space Telescope utilizes mercury-cadmium telluride detector rays cooled to approximately 7 Kelvin, achieving quantum efficiencies exceeding 80% across crucial infrared wavelengths. These detectors can measure brightness variations as small as 10 parts per million, essential for detecting the minute atmospheric signatures of transiting exoplanets. Spectroscopic techniques have evolved to provide unprecedented resolving power and wavelength coverage for atmospheric analysis. Webb's near-infrared spectrograph achieves spectral resolution up to or equals 3000, enabling precise identification of molecular absorption lines even in complex atmospheric mixtures. Advanced grating technologies and sophisticated optical designs allow simultaneous observation across broad wavelength ranges, maximizing the scientific information extracted from each observation. Data processing algorithms have revolutionized the extraction of planetary signals from stellar observations. Modern techniques employ sophisticated statistical methods to remove stellar variability, instrumental effects, and systematic noise sources that previously limited atmospheric detection capabilities. Machine learning approaches can identify subtle patterns in spectroscopic data that might escape traditional analysis methods, enhancing detection sensitivity for trace atmospheric constituents. Atmospheric modeling software has reached levels of sophistication that enable detailed interpretation of observed spectroscopic signatures. Three-dimensional climate models incorporate atmospheric circulation, cloud formation, chemical kinetics, and radiative transfer to predict observable signatures for different atmospheric compositions and planetary conditions. These models provide the theoretical framework necessary to distinguish biological from abiotic explanations for observed atmospheric chemistry. Instrument stability and calibration techniques ensure measurement precision adequate for detecting biosignatures in exoplanet atmospheres. Webb's instruments undergo extensive on-orbit calibration using stellar standards and internal reference sources to maintain wavelength accuracy within fractions of a pixel. Temperature control systems maintain detector stability to parts per million over observation timescales spanning several hours. The development of coronagraphic techniques promises even greater capabilities for future exoplanet observations. Advanced starlight suppression methods could enable direct imaging of exoplanet atmospheres, providing access to non-transiting worlds and enhanced sensitivity for atmospheric characterization. Segmented telescope designs and adaptive optics systems continue to push the boundaries of angular resolution and contrast ratios achievable from space-based platforms. Cryogenic cooling technology enables the ultra-low operating temperatures essential for infrared astronomy. Webb's passive cooling system, combined with mechanical cryocoolers, maintains instrument temperatures below 7 Kelvin throughout the mission lifetime. These thermal conditions minimize instrumental noise sources and enable detection of the faint thermal signatures characteristic of temperate exoplanets. Real-time data analysis capabilities allow rapid identification of interesting targets and optimization of observational strategies. Automated pipeline processing can analyze Webb observations within hours of data acquisition, enabling prompt follow-up observations when favorable conditions arise. This rapid response capability maximizes the scientific return from limited telescope time and increases the probability of detecting transient phenomena. Collaborative observation networks coordinate ground-based and space-based assets to provide comprehensive coverage of exoplanet events. International partnerships enable round-the-clock monitoring of target systems and coordination of complementary observations using different techniques. These collaborative efforts multiply the effective observing capabilities and provide independent confirmation of significant discoveries. The miniaturization of space-based instruments promises expanded capabilities for future exoplanet missions. CubeSat technologies could enable constellation approaches to exoplanet monitoring, providing continuous coverage and enhanced temporal resolution for atmospheric variability. Studies. Distributed observing systems might achieve sensitivity levels comparable to much larger single-aperture telescopes through interferometric combination of signals. Artificial intelligence applications continue to transform exoplanet data analysis by identifying patterns and correlations that exceed human analytical capabilities. Neural network approaches can process vast datasets to identify candidate biosignatures, classify atmospheric types, and predict optimal targets for follow-up observations. These techniques promise to accelerate the pace of discovery and enable analysis of increasingly complex datasets. Future technological developments will further enhance our capacity to detect and characterize potentially habitable worlds. Next-generation space telescopes with larger apertures and enhanced spectroscopic capabilities will enable atmospheric analysis of Earth-sized planets around Sun-like stars. Advanced detector technologies and improved observational techniques will push detection thresholds to levels where comprehensive atmospheric inventories become possible. For a broad range of exoplanet types, astrobiology and the search for life, the discovery of potential biosignatures on K2-18b fundamentally transforms our understanding of life's distribution throughout the universe and provides crucial insights into the conditions that might support biological evolution beyond Earth. This breakthrough represents more than an isolated finding. It demonstrates that the techniques and theoretical frameworks developed for detecting extraterrestrial life can successfully identify biological activity on distant worlds. The prevalence of subneptune planets throughout the galaxy suggests that K2-18b might represent just one example of a much larger population of potentially habitable worlds. Current estimates indicate that subneptunes comprise roughly 30% of all exoplanets, with billions of such worlds orbiting within the habitable zones of their host stars. If even a small fraction of these planets maintain conditions suitable for life, the universe could contain countless living worlds waiting to be discovered. The detection of biosignatures on a red dwarf star carries particular significance because these stellar types dominate galactic populations. Red dwarfs comprise approximately 75% of all main sequence stars, and their extreme longevity provides extended timeframes for biological evolution. The confirmation that life can flourish on planets orbiting red dwarf stars expands the potential habitable real estate of the galaxy by an order of magnitude compared to previous estimates. Based solely on Sun-like stars, the atmospheric chemistry observed on K2-18b provides insights into alternative biochemistries that might operate under different planetary conditions. The specific combination of gases detected suggests metabolic pathways that could differ from those familiar on Earth, potentially indicating that life adapts to utilize available chemical resources and energy sources. This adaptability implies that biological processes might emerge under a broader range of conditions than previously thought possible. The discovery validates theoretical predictions about atmospheric biosignatures and demonstrates the effectiveness of current detection strategies. The successful identification of dimethyl sulfide and other biological indicators confirms that space-based observatories can distinguish living worlds from sterile planets using existing technology. This validation provides confidence for expanding biosignature surveys to larger samples of potentially habitable exoplanets. The implications extend beyond pure science to influence humanity's long-term perspective on space exploration and our cosmic future. The confirmation of life beyond our solar system fundamentally alters the context for human space exploration by providing concrete targets for detailed investigation. Future missions might prioritize systems like K2-18 for comprehensive study, potentially including robotic probes designed to search for additional biosignatures or even direct evidence of biological activity. The discovery raises profound questions about the nature and complexity of extraterrestrial life. The detected biosignatures indicate active biological processes but provide limited information about the complexity or evolutionary development of K2-18b's biosphere. The organisms could range from simple microbial communities to complex multicellular ecosystems, representing vastly different implications for our understanding of biological evolution and the likelihood of intelligence emerging elsewhere in the universe. Technological developments motivated by this discovery will likely accelerate progress in related fields, including atmospheric chemistry, climate modeling, and detector technology. The success of Webb's biosignature detection capabilities will inform the design of future space telescopes specifically optimized for characterizing potentially habitable worlds. Enhanced sensitivity and spectral coverage could enable detection of even more subtle biological indicators on a broader range of planetary types. The societal implications of confirming extraterrestrial life cannot be overstated, potentially influencing philosophy, religion, and humanity's collective self-perception. The knowledge that Earth is not unique in harboring life might inspire greater environmental stewardship of our own planet while fostering international cooperation in space exploration efforts. The discovery could serve as a unifying force for humanity, emphasizing our shared cosmic heritage and common interest in understanding our place in the universe. International policy considerations will likely emerge regarding the protection and study of potentially inhabited worlds. The development of planetary protection protocols could prevent contamination of extraterrestrial biospheres while ensuring that human exploration activities do not interfere with indigenous biological processes. These considerations might influence the design and implementation of future interstellar missions. The economic implications of confirmed extraterrestrial life could drive substantial investments in space technology and exploration capabilities. Private sector interest in astrobiology research might accelerate technological development while government space agencies prioritize missions to potentially inhabited systems. The discovery could catalyze a new era of space exploration focused on biological rather than purely physical or geological investigations. Educational and outreach implications emphasize the importance of scientific literacy and public understanding of astrobiology research. The discovery provides compelling evidence for the value of basic scientific research and international collaboration in advancing human knowledge. Educational curricula might incorporate astrobiology concepts to inspire future generations of scientists and engineers. Exoplanet exploration. The successful detection of biosignatures on K2-18b marks the beginning of a new era in exoplanet science, one characterized by the systematic search for life beyond our solar system. The techniques and technologies that enabled this groundbreaking discovery provide a foundation for expanded surveys that could identify hundreds of potentially inhabited worlds within the next decade. The James Webb Space Telescope's remaining operational lifetime offers opportunities to study dozens of additional exoplanet atmospheres with the same level of detail achieved for K2-18b. Priority targets include other sub-Neptune worlds orbiting within habitable zones, terrestrial planets around nearby red dwarf stars, and unusual atmospheric compositions that might indicate exotic forms of biological activity. Each successful atmospheric characterization expands our understanding of planetary diversity and habitability. Future space telescope missions currently under development will provide enhanced capabilities for exoplanet atmospheric analysis. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, includes coronagraphic instruments capable of directly imaging exoplanet atmospheres without requiring planetary transits. This capability will enable atmospheric studies of non-transiting worlds and provide access to planets orbiting at larger distances from their host stars. Ground-based observatories continue to play crucial roles in exoplanet discovery and initial characterization. The extremely large telescopes currently under construction will achieve unprecedented angular resolution and light-gathering power, enabling atmospheric studies of nearby exoplanets through direct observation techniques. These facilities will complement space-based observations by providing continuous monitoring capabilities and rapid response to transient phenomena. Technological developments in detector sensitivity and spectroscopic resolution promise even greater precision in future atmospheric measurements. Next-generation infrared detectors could achieve quantum efficiencies approaching 100% while operating at higher temperatures, reducing cooling requirements and enabling more compact instrument designs. Advanced spectroscopic techniques might resolve individual molecular absorption lines, providing detailed information about atmospheric temperature, pressure, and circulation patterns. Artificial intelligence applications will increasingly automate the discovery and analysis of potentially habitable exoplanets. Machine learning algorithms can process vast data sets from survey missions to identify candidate biosignatures, classify atmospheric types, and prioritize targets for detailed follow-up observations. These automated approaches will enable analysis of much larger planetary samples than possible through traditional manual methods. International collaboration in exoplanet research continues to expand, with space agencies worldwide contributing complementary capabilities and expertise. Coordinated observation campaigns enable comprehensive characterization of individual targets, while shared data archives maximize the scientific return from each mission. Future international partnerships might support ambitious projects such as space-based interferometer networks capable of achieving extraordinary angular resolution and sensitivity. The development of interstellar probe technologies represents the ultimate goal for studying potentially inhabited exoplanets. Breakthrough Starshot and similar initiatives aim to develop ultra-lightweight spacecraft capable of reaching nearby star systems within decades rather than millennia. Such missions could provide close-up observations of exoplanet atmospheres and surfaces, potentially detecting direct evidence of biological activity through high-resolution imaging and spectroscopy. Target selection strategies for future observations will prioritize systems with the highest probability of harboring detectable biosignatures. Statistical analyses of exoplanet populations guide the identification of optimal stellar types, planetary characteristics, and orbital configurations for biosignature searches. The experience gained from K-18 observations will inform refined target selection criteria that maximize the probability of successful life detection. Atmospheric modeling capabilities continue to advance, incorporating increasingly sophisticated treatments of chemistry, circulation, and cloud formation processes. Three-dimensional global circulation models coupled with detailed chemical kinetics enable accurate predictions of observable signatures for different biological scenarios. These models guide observational strategies and provide frameworks for interpreting complex atmospheric measurements. The search for technosignatures represents an emerging frontier in exoplanet science, focusing on artificial signatures that might indicate technologically advanced civilizations. Radio telescope arrays and optical observatories scan for patterns that suggest intelligent manipulation of planetary environments or deliberate communication attempts, while more speculative than biosignature searches. Technosignature investigations could reveal even more profound implications for humanity's place in the universe. Long-term vision for exoplanet exploration includes comprehensive surveys that catalog the atmospheric properties of thousands of potentially habitable worlds. Statistical analyses of large planetary samples will reveal the frequency of different atmospheric types and the prevalence of biosignatures throughout the galaxy. These surveys will provide crucial data for understanding the factors that control planetary habitability and the likelihood of life emerging under different conditions. The integration of exoplanet science with other astronomical disciplines continues to reveal new insights about planetary formation, stellar evolution, and galactic chemical evolution. Understanding how planetary systems form and evolve provides context for interpreting atmospheric observations and predicting which worlds might maintain habitable conditions over cosmic timescales. This interdisciplinary approach enhances our capacity to identify and characterize potentially living worlds, challenges, and limitations. Despite the remarkable success in detecting potential biosignatures on K-18b, significant challenges and limitations constrain our current ability to confirm extraterrestrial life with absolute certainty. NTA. Understanding these constraints provides important context for interpreting existing observations while highlighting areas where technological and methodological advances could enhance future discoveries. Observational limitations impose fundamental constraints on the types of atmospheric signatures that can be detected using current instruments. The James Webb Space Telescope, despite its unprecedented capabilities, requires favorable geometric alignments where planets transit in front of their host stars as viewed from Earth. This geometric requirement restricts observations to a small fraction of exoplanets, potentially missing many inhabited worlds that do not undergo transits from our perspective. Spectral resolution limitations affect the precision with which individual molecular species can be identified and quantified in exoplanet atmospheres. While Webb spectrographs provide sufficient resolution to detect major atmospheric constituents, distinguishing between closely related molecules or identifying trace species requires even higher spectral resolution than currently available. Enhanced resolution could enable detection of isotopic ratios that provide stronger evidence for biological processes. Signal-to-noise limitations constrain the detection thresholds for weak atmospheric signatures, particularly for smaller planets or those orbiting brighter stars where stellar contamination becomes problematic. Current observations require favorable combinations of planetary size, stellar brightness, and atmospheric opacity to achieve sufficient sensitivity for biosignature detection. Many potentially habitable worlds remain beyond the detection capabilities of existing instruments. Temporal sampling limitations restrict our ability to monitor atmospheric variability that might provide additional evidence for biological activity. Space telescopes have limited observing time available for any individual target, preventing comprehensive monitoring of seasonal changes or temporal variations in atmospheric composition. Continuous monitoring over extended periods could reveal biological rhythms or responses to environmental changes. Atmospheric modeling uncertainties introduce ambiguities in interpreting observed spectroscopic signatures. Complex interactions between atmospheric chemistry, circulation patterns, and cloud formation processes create numerous possible explanations for specific observational signatures. Current models may not capture all relevant physical processes, particularly for planetary conditions significantly different from those found in our solar system. False positive scenarios represent ongoing challenges in distinguishing biological from abiotic sources of apparent biosignatures. Geological processes, atmospheric photochemistry, and stellar activity can sometimes produce chemical signatures that superficially resemble biological indicators. Ruling out these alternative explanations requires comprehensive understanding of planetary physics and chemistry under diverse conditions. Contamination concerns affect both observational data and theoretical interpretations of atmospheric measurements. Instrumental artifacts, data processing errors, or interference from extraneous sources could create spurious signals that mimic biosignatures. Extensive calibration procedures and independent confirmation help minimize these risks, but complete elimination of contamination sources remains challenging. Statistical uncertainties limit the confidence levels that can be assigned to biosignature detections based on current observational techniques. Single-molecule detections carry inherent ambiguities due to potential false positives, while multiple independent signatures provide stronger evidence but remain subject to systematic errors or correlated uncertainties. Achieving definitive confirmation of extraterrestrial life requires reducing these statistical uncertainties through improved measurements and analysis techniques. Theoretical limitations in our understanding of alternative biochemistries constrain our ability to predict all possible biosignatures that extraterrestrial life might produce. Earth-based biology provides limited examples of the chemical processes that living systems might employ under different environmental conditions. Expanding the catalog of potential biosignatures requires theoretical advances in biochemistry and metabolic pathway analysis. Technological constraints limit the sensitivity and wavelength coverage of current space-based observatories. Detector noise, optical imperfections, and thermal emission from warm telescope components establish fundamental detection limits that cannot be overcome through improved data processing techniques. Next-generation instruments with larger apertures, enhanced detectors, and better thermal control will be required to achieve substantial improvements in sensitivity. Interplanetary distances create communication delays and coordination challenges for responsive observations of time-variable phenomena. Space telescopes cannot be rapidly reconfigured to respond to unexpected atmospheric changes or transient events that might provide crucial evidence for biological activity. Pre-planned observation strategies must anticipate potential discoveries without the flexibility to adapt to emerging results. Resource allocation constraints limit the number of targets that can be studied in detail using premium space-based facilities. The James Webb Space Telescope's observing time is heavily oversubscribed. With demand far exceeding available observational capacity, priority must be given to targets with the highest probability of yielding definitive results. potentially missing serendipitous discoveries on less obvious targets. K218b. The discovery of potential biosignatures on K218b provides crucial data for understanding how life might be distributed throughout our galaxy and what factors control the emergence and persistence of biological activity on planetary scales, placing this discovery within the broader context of galactic evolution and planetary formation reveals important insights about the cosmic prevalence of habitable environments. The Milky Way galaxy contains an estimated 100 to 400 billion stars, with current surveys suggesting that virtually every star hosts at least one planet. This vast planetary population includes billions of worlds orbiting within their host stars' habitable zones, where liquid water can potentially exist on planetary surfaces. The detection of biosignatures on K218b suggests that a significant fraction of these potentially habitable worlds might actually support biological activity. Stellar population characteristics significantly influence the distribution of habitable planets throughout the galaxy. Red dwarf stars like K218 dominate the stellar census, comprising roughly 75% of all main sequence stars in our galactic neighborhood. The extreme longevity of red dwarf stars, with main sequence lifetimes exceeding 100 billion years, provides extended opportunities for biological evolution that far exceed the timescales available on more massive stars. The metallicity distribution of stars throughout the galaxy creates regional variations in planetary formation efficiency and composition. Stars with higher abundances of elements heavier than hydrogen and helium can form terrestrial planets more readily and with greater diversity of chemical compositions. The galactic metallicity gradient suggests that habitable planets might be more common in the inner regions of the galaxy, where successive generations of stellar nucleosynthesis have enriched the interstellar medium. Galactic chemical evolution influences the availability of elements essential for biological processes, including carbon, nitrogen, oxygen, phosphorus, and sulfur. The cosmic abundance of these biogenic elements has increased over cosmic time as stellar nucleosynthesis and supernovae have progressively enriched the galaxy with heavy elements. Planets forming in the current epoch have access to greater inventories of biogenic materials than worlds that formed during the galaxy's early history. The galactic habitable zone concept suggests that certain regions of the Milky Way might be more conducive to the emergence and persistence of life than others. This zone balances the need for sufficient heavy element abundances to form terrestrial planets against the risks posed by energetic events such as supernovae, gamma-ray bursts, and stellar encounters that could disrupt planetary systems or sterilize biospheres. Stellar encounter frequencies vary throughout the galaxy depending on local stellar density and orbital dynamics. The solar system's location in the galactic disk provides relatively stable conditions with infrequent close encounters that could disrupt planetary orbits. Dense stellar environments such as globular clusters or the galactic center experience much higher encounter rates that might destabilize planetary systems and prevent the long-term stability required for biological evolution. The cosmic ray environment varies significantly throughout the galaxy, potentially affecting the habitability of planetary surfaces and atmospheres. Regions with enhanced cosmic ray fluxes, such as areas near supernova remnants or active galactic nuclei, might experience elevated radiation levels that could sterilize planetary surfaces or strip away atmospheric protection. Understanding these environmental factors helps constrain where habitable conditions can persist over cosmic timescales. The timing of planet formation relative to galactic chemical evolution influences the potential for habitability. Planets forming too early in galactic history might lack sufficient heavy elements to develop complex chemistry and stable climates. Conversely, planets forming in metal-rich environments might experience enhanced greenhouse effects or other compositional extremes that preclude habitability. The optimal timing for habitable planet formation likely occurred within the last 6 to 8 billion years. The distribution of planet types throughout the galaxy depends on the detailed physics of planetary formation and migration processes. Sub-Neptune planets like K218b appear to be extremely common around red dwarf stars, suggesting that this planet type might represent the most abundant potentially habitable environment in the galaxy. Understanding the formation mechanisms for subneptunes provides insights into how commonly these worlds might develop conditions suitable for life. The role of planetary system architecture in determining habitability includes factors such as the presence of giant planets, asteroid belts, and stellar companions that can influence planetary climates and impact rates. Systems with favorable architectures might maintain stable habitable conditions over extended periods, while less favorable configurations could experience frequent catastrophic impacts or extreme climate variations that prevent biological evolution. The discovery of biosignatures on K-1AP suggests that the galaxy might contain countless inhabited worlds, potentially numbering in the billions. This possibility fundamentally alters humanity's perspective on our cosmic significance and the prevalence of life throughout the universe, if confirmed through additional observations. The detection of extraterrestrial life would represent one of the most profound discoveries in human history. Statistical projections based on current exoplanet surveys and the K-1AP discovery suggest that habitable worlds might exist within a few dozen light-years of Earth. Future technological advances in telescope capabilities and detection techniques could enable comprehensive surveys of nearby stellar systems to search for additional biosignatures. Such surveys might reveal that life is a common outcome of planetary evolution rather than an extraordinary accident unique to Earth. The implications extend beyond academic interest to influence long-term planning for human space exploration and the search for extraterrestrial intelligence. The confirmation of nearby inhabited worlds could motivate development of interstellar travel technologies and communication protocols for potential contact with extraterrestrial civilizations. The discovery represents a crucial step toward understanding humanity's place within a potentially vast cosmic community of living worlds. Chapter 11: Technological and Scientific Implications. The confirmation of biosignatures on K-1AP catalyzes a cascade of technological developments and scientific investigations that extend far beyond exoplanet astronomy. This groundbreaking discovery drives innovation across multiple disciplines while establishing new paradigms for understanding life's cosmic distribution and the technological capabilities required to study potentially inhabited worlds. Advanced spectroscopic techniques developed for exoplanet atmospheric analysis find applications in Earth-based environmental monitoring, industrial process control, and medical diagnostics. The ultra-sensitive detection methods pioneered for biosignature identification enable precise measurement of trace atmospheric constituents relevant to climate change research, pollution monitoring, and atmospheric chemistry studies. These technological spillovers demonstrate how space exploration drives innovation with terrestrial applications. Detector technology advances motivated by the need for enhanced biosignature sensitivity influence developments in medical imaging, materials science, and fundamental physics research. The mercury-cadmium telluride detector arrays optimized for Webb's infrared observations contribute to advances in thermal imaging systems, night vision equipment, and astronomical instrumentation for ground-based observatories. Continued improvements in detector quantum efficiency and noise characteristics benefit numerous scientific and commercial applications. Computational capabilities required for processing and analyzing vast exoplanet datasets drive developments in machine learning, pattern recognition, and statistical analysis techniques. The algorithms developed for identifying subtle biosignatures in complex spectroscopic data contribute to advances in medical diagnosis, financial analysis, and environmental monitoring applications. These computational tools enable extraction of meaningful information from increasingly complex and voluminous datasets across diverse fields. International collaboration frameworks established for coordinating exoplanet observations provide models for addressing other global challenges requiring multinational cooperation. The protocols developed for sharing telescope time, standardizing data formats, and coordinating observation strategies contribute to collaborative approaches in climate research, space exploration, and fundamental physics investigations. These frameworks demonstrate the effectiveness of international scientific cooperation The discovery motivates substantial investments in next-generation space telescope technology, driving advances in large aperture construction, cryogenic cooling systems, and precision pointing control, future observatories designed specifically for Exoplanet. Characterization will incorporate lessons learned from Webb's success while pushing technological boundaries further. These investments accelerate the development of space-based platforms for diverse scientific applications. Atmospheric modeling capabilities enhanced for interpreting exoplanet observations contribute to improved climate models for Earth and other solar system bodies. The sophisticated treatment of radiative transfer, chemical kinetics, and circulation dynamics developed for analyzing alien atmospheres provides insights applicable to understanding terrestrial climate change, planetary formation processes, and atmospheric evolution throughout the solar system. The validation of biosignature detection techniques establishes confidence in our ability to identify extraterrestrial life using remote sensing methods. This capability influences strategies for future missions to potentially habitable solar system bodies such as Mars, Europa, and Enceladus, where similar techniques might detect biosignatures in atmospheric or surface compositions. The success builds momentum for expanded astrobiology research programs. Educational implications include the development of new curricula emphasizing astrobiology, planetary science, and the interdisciplinary approaches required for studying potentially inhabited worlds. The discovery provides compelling examples for inspiring student interest in science, technology, engineering, and mathematics fields while demonstrating the practical value of basic scientific research. Educational institutions worldwide incorporate exoplanet science into academic programs at all levels. Economic implications encompass the growth of space technology industries, the development of new scientific instrumentation markets, and the potential for space-based manufacturing and resource utilization. The success of Exoplanet research demonstrates the commercial potential of advanced space technologies while creating demand for enhanced capabilities in related fields. Private sector investment in space exploration accelerates as the potential for discovering inhabited worlds becomes more concrete. Policy implications include the need for developing international frameworks governing the study and potential contact with extraterrestrial life. The discovery of biosignatures raises questions about planetary protection protocols, scientific data sharing agreements, and the responsibilities of nations discovering potentially inhabited worlds. These considerations influence space law development and international cooperation agreements. Philosophical implications challenge traditional human-centered worldviews and encourage broader perspectives on life's cosmic significance. The confirmation of extraterrestrial biology fundamentally alters humanity's understanding of our place in the universe while raising profound questions about the nature of life, consciousness, and intelligence. These considerations influence fields ranging from ethics and theology to psychology and sociology. Future technological developments motivated by exoplanet research include advances in artificial intelligence, quantum computing, and advanced materials science. The computational challenges associated with analyzing complex atmospheric data drive developments in quantum algorithms and neuromorphic computing architectures. Materials science advances support the development of larger, lighter space telescopes and more sensitive detector systems. The discovery establishes precedents for international scientific cooperation and data sharing that benefit numerous other research areas. The open access policies and collaborative frameworks developed for exoplanet research provide models for addressing challenges in climate science, global health, and fundamental physics research. These collaborative approaches maximize the scientific return from international investments in research infrastructure. Long-term implications include the potential development of interstellar communication protocols and the preparation for eventual contact with extraterrestrial civilizations. While the detected biosignatures indicate microbial or simple multicellular life rather than technological intelligence, the discovery represents a crucial first step toward understanding the prevalence of life Throughout the galaxy, this understanding influences humanity's long-term vision for space, exploration, and our cosmic future. The confirmation of biosignatures on K218b represents a technological watershed that reverberates across multiple scientific disciplines, engineering fields, and societal institutions. This discovery validates decades of investment in space-based astronomy while demonstrating the profound interconnections between fundamental research and technological innovation. The cascade of developments triggered by this breakthrough extends far beyond astronomy, influencing everything from medical diagnostics to artificial intelligence development. The infrared spectroscopy techniques refined for exoplanet atmospheric analysis find immediate applications in Earth-based environmental monitoring systems. The ultra-sensitive detection methods capable of identifying trace atmospheric constituents at parts per billion concentrations enable revolutionary advances in pollution monitoring, industrial emissions tracking, and atmospheric chemistry research. Environmental agencies worldwide adopt these technologies for real-time monitoring of greenhouse gases, industrial pollutants, and atmospheric aerosols with unprecedented precision and temporal resolution. Medical imaging technologies benefit substantially from detector advances urgently developed for space-based astronomy. The mercury-cadmium telluride detector arrays optimized for Webb's infrared observations contribute to breakthrough developments in thermal imaging systems for medical diagnostics. These enhanced detectors enable non-invasive detection of inflammatory conditions, circulatory disorders, and metabolic abnormalities through precise measurement of tissue temperature variations and blood flow patterns invisible to conventional imaging techniques. The data processing algorithms developed for extracting planetary signals from stellar observations revolutionize pattern recognition capabilities across diverse fields. Financial institutions adopt these statistical techniques for fraud detection, market analysis, and risk assessment applications that require identification of subtle patterns in massive datasets. The machine learning approach is originally designed to distinguish biological from abiotic atmospheric signatures proven valuable for medical diagnosis systems that must differentiate between healthy and pathological conditions based on complex biomarker patterns. Artificial intelligence development accelerates dramatically as researchers apply the sophisticated pattern recognition algorithms developed for biosignature detection to increasingly complex real-world problems. The neural network architectures optimized for analyzing multispectral atmospheric data contribute to advances in autonomous vehicle navigation, industrial quality control, and scientific data analysis across disciplines. These AI systems demonstrate unprecedented capabilities for extracting meaningful information from high-dimensional datasets that exceed human analytical capacity. The precision control systems developed for space telescope pointing and stability find applications in manufacturing, robotics, and precision instrumentation. The nanometer scale positioning accuracy required for maintaining stellar pointing during exoplanet observations translates directly to enhanced capabilities for semiconductor manufacturing, precision machining, and scientific instrumentation. These technological advances enable manufacturing processes with tolerances previously considered impossible while supporting the development of quantum computing systems and advanced scientific instruments. International collaboration frameworks established for coordinating exoplanet observations provide models for addressing global challenges that require multinational cooperation and resource sharing. The protocols developed for sharing telescope time, standardizing data formats, and coordinating observation campaigns influence collaborative approaches in climate research, pandemic response, and global security applications. These frameworks demonstrate the effectiveness of international scientific cooperation while establishing precedents for addressing challenges that transcend national boundaries. The cryogenic cooling technologies pioneered for space-based infrared astronomy contribute to advances in quantum computing, superconducting electronics, and fundamental physics research. The mechanical refrigeration systems capable of maintaining temperatures below 10 Kelvin in space environments enable terrestrial applications requiring ultra-low temperatures for optimal performance. These cooling technologies support the development of quantum computers, particle physics experiments, and advanced medical imaging systems that rely on superconducting components. Educational transformation occurs at all levels as institutions worldwide recognize the interdisciplinary nature of modern scientific research and the importance of technological innovation for addressing complex challenges. Engineering curricula incorporate astrobiology concepts, while biology programs include planetary science components to prepare students for careers in emerging interdisciplinary fields. The discovery demonstrates the practical value of basic scientific research while inspiring student interest in science, technology, engineering, and mathematics disciplines. The materials science advances required for constructing large space telescopes influence diverse terrestrial applications ranging from construction and transportation to consumer electronics. The lightweight, high-strength materials developed for telescope mirrors and support structures contribute to advances in automotive manufacturing, aerospace engineering, and renewable energy systems. Carbon fiber composites, advanced ceramics, and precision metal alloys developed for space applications enable terrestrial technologies with enhanced performance and reduced environmental impact. Computational fluid dynamics capabilities enhanced for modeling exoplanet atmospheres contribute to advances in weather prediction, climate modeling, and engineering design applications. The sophisticated atmospheric circulation models developed for understanding tidally locked planets provide insights applicable to terrestrial weather systems, ocean circulation patterns, and industrial fluid dynamics problems. These computational tools enable more accurate predictions of severe weather events while supporting the design of more efficient aircraft, wind turbines, and industrial systems. The discovery motivates substantial investments in quantum sensing technologies that could enable even more sensitive detection of trace atmospheric constituents and other faint signals. Quantum sensors based on atomic interferometry, nitrogen vacancy centers in diamond, and superconducting quantum interference devices promise order of magnitude improvements in sensitivity for magnetic field detection, gravitational measurements, and chemical sensing applications. These technologies influence fundamental physics research while enabling practical applications in navigation, medical diagnosis, and environmental monitoring. Biotechnology research expands to encompass the study of extremophile organisms that might provide insights into the types of life that could exist under the harsh conditions found on exoplanets. Laboratory investigations of organisms that thrive under high pressure, intense radiation, and exotic chemical environments reveal previously unknown biochemical pathways and survival mechanisms. These discoveries contribute to advances in pharmaceutical development, biofuel production, and environmental remediation while expanding our understanding of life's fundamental limits and adaptation. Abilities. The optical technologies developed for space-based coronagraphy influence advances in medical imaging, manufacturing inspection, and security applications. The techniques for suppressing bright light sources to reveal faint nearby objects translate directly to medical applications such as retinal imaging, where bright reflections must be suppressed to visualize subtle pathological changes. Manufacturing industries adopt these optical techniques for quality control applications that require detection of minute surface defects or contamination particles. Communication systems designed for coordinating international observatory networks contribute to advances in global telecommunications, internet infrastructure, and distributed computing systems. The protocols developed for ensuring reliable data transmission and real-time coordination between widely separated facilities influence the design of next-generation internet architectures, satellite communication systems, and distributed scientific computing networks. These communication advances support increasingly complex global collaborations while enabling new forms of international cooperation. The statistical analysis techniques developed for assessing the significance of potential biosignatures influence diverse fields that require robust interpretation of complex datasets. Medical research adopts these statistical frameworks for evaluating treatment efficacy and diagnostic accuracy, while environmental science applies them to assess the significance of pollution trends and ecosystem changes. The rigorous standards developed for extraordinary claims about extraterrestrial life provide models for evaluating evidence in other fields where false positive risks carry significant consequences. Advanced manufacturing techniques required for constructing precision space instruments contribute to developments in consumer electronics, medical devices, and renewable energy systems. The ultra-precision machining capabilities needed for telescope mirrors and spectrograph components enable manufacturing of consumer products with enhanced performance and reliability. Medical device manufacturers adopt these precision manufacturing techniques for producing implants, surgical instruments, and diagnostic equipment with tolerances and surface finishes previously unattainable. The discovery catalyzes research into alternative energy systems that might be required for long-duration space missions to study potentially habitable exoplanets. Advanced nuclear power systems, solar concentrators, and energy storage technologies developed for space applications influence terrestrial energy systems and contribute to the transition toward renewable energy sources. These technologies provide enhanced efficiency and reliability for both space exploration and terrestrial energy applications while reducing dependence on fossil fuels.